Good afternoon, dear all. Welcome to the new course to IMP 40, Applications of Data Science to Software Engineering. Alexander Serebrenik. I'm professor of social software engineering in the Software Engineering and Technology group, and I'm a responsible lecturer of this course. This lecture is going to be recorded. After the lecture, you will receive a link to where you can find the recording. But of course, I will still appreciate you being present during the lectures, because in this way you can influence what we are going to discuss, how we are going to discuss, and so on. So let us start with the more formal and more boring stuff, such as administration. So I hope that all of you have found a way to Osiris. This is a description of the course on Osiris. At least this is how it looked a couple of weeks ago. It contains a lot of information. The most important parts are probably those ones. So first of all, it's a 5 ECTS course, as any other course offered by our master's program. And this means that an average student should spend roughly 140 hours for the entire course. So 140 hours will consist of 28 hours of lectures and 112 hours of homework. Of course, this is merely an estimate. Some students need more time, some students need less time, some students find certain aspects more challenging than others. So this is an estimate. So if you are going slightly above or below this effort investment, that's fine. If you are significantly above or below, please let me know. You can always contact me by email or by phone, and we are going to meet on the so-called E1 slot, which is for normal human being means Tuesday afternoon, like today, from 1:30 till 3:15, and Thursday morning from 8:45 till 10:30. And we are not going to have classes during the Christmas break, meaning the last 2 weeks of December. There will be no classes. So after you have taken this class, you should be able to do several things, which I hope will help you also in other subjects you are going to take afterwards. So first of all, you will be expected to be able to formulate and motivate research questions to the extent that they pertain to software engineering. And among those research questions, you should be able to identify which questions can and which questions cannot be answered by means of empirical research. We are going to discuss this topic already today. Then, given the research question you want to get answered, you should be able to compare different research designs and research methods. Every single research strategy, every single research method we are going to discuss has its own strengths and weaknesses, and usually there is not a single way to answer a research question at hand. So hopefully, after you have taken this class, you should be able to discuss different research questions, different research methods given your research question, understand their strengths, understand their weaknesses, and how you can combine them. The next step would be to design an empirical study. So in a way, it is not enough for you to say, okay, I would like to conduct a judgment study, or I would like to conduct a field experiment. You also need to understand what kind of research methods are useful for those strategies and how to organize your actual study. So for instance, if you would like to conduct a survey, you should know what kind of questions to ask, what kind of people to target, how to reach those people, what kind of problems can arise if you are phrasing your questions in an appropriate way, and so on. So you should be able to choose an appropriate method, and you should be able to defend your choice. Of course, once you have decided what you want to do and how you want to do, the next step is actually to do, right? So essentially, this means that you need to actually design a survey or design an interview guide. If you want to conduct a controlled experiment, you need to be able to design tasks and so on and so forth. So most of the time, we are not going to apply those things in practice because it's simply not practical given the scope of the course, but you should be able to design and pilot the instruments you want to use. On the other part of the story, once you have applied your research methods, of course, you get some kind of data, some kind of output of your study, and you need to be able to draw conclusions based on this empirical data. So you need to interpret what you have seen, what does this mean from the software engineering perspective, and how to deal with the concerns which might have threatened validity of your conclusions. And then, of course, all this should be presented in writing. So communication, our primary communication channel is Slack. I hope that all of you have found it by now. If not, this is a link. Slack has multiple channels. It has a channel for lectures. It has a channel for assignments. It also has an introduction channel. And I would really like to ask you to say a couple of words about who you are and why have you chosen this course and what do you expect from this course in the introduction channel. Knowing your expectations and understanding your expectations will help us to tailor this course to your needs to the extent we can do it. Please do not mail me simply because I'm getting a whole bunch of emails. So unless you, it's really something which you feel it cannot be discussed by Slack, please do not mail me. Slack has private channels. So if you want to talk to me one-to-one, or if you would like to talk to Nathan and to me, please create a private channel. Canvas and Osiris, as usual, Canvas will have slides, assignments, announcements. Canvas is also where those conferences take place. And of course, your final grade will be on Osiris. So talking of the grading, the assessment will consist of essentially two parts. We will have weekly quizzes. Quizzes will be released on Thursday after a lecture, after the lecture on Thursday, so around 10:30. And you should submit them on Tuesday before the lecture. So essentially you have almost the entire Thursday, Friday, Monday, and half of a Tuesday to answer those quizzes. One of those quizzes is kind of special. It's not really a quiz, but on December 3, we will attend the Belgium-Netherlands Software Evolution Workshop, also known as Benevol. The workshop, the time slot of the workshop coincides with the time slot of our lecture on Thursday morning. I will provide more information about this workshop and about what the program will be as it will be announced by the workshop organizers. But the intention is that you will attend one or more talks and submit a summary. The summary would count as a quiz, and we will grade it on the scale fail, pass, and good. So both weekly quizzes and Benevol summaries are individual. And then on top of this, you will be required to perform one large assignment. This assignment will also be individual. It should be an empirical paper about equity, diversity, and inclusion in software engineering. We're going to see quite some examples of this kind of research during the course. And this assignment will consist of two parts. In the first part, you will be requested to formulate research questions and motivate them. This part is not going to be graded, but we will provide you the feedback because we would like to help you as much as possible in phrasing those research questions and in explaining us in a convincing way why those questions are important and for whom. And then based on this feedback, you should revise part one and extend your document to include the actual design of a study. So which methods you're going to use in order to collect the data, which methods you're going to use in order to analyze the data, and what kind of threads are involved in this kind of analysis. So grading, the formulas are on the slide. A is an assignment grade. Is it known at, sorry, there is a question in the chat. Is this known at this time that the Beneville workshop is going to be in person or online? Yes, the workshop is online. So you don't need to travel anywhere. It's just, okay. Grading, A is the grade for this final assignment. Q is the median of the quiz grades. So essentially, we are going to look at the grades for quizzes. We are going to compute the median, and we are going to compute the final grade based on those two formulas. Essentially, if you fail the assignment part, the large assignment part, you can never get more than 5. This means that you fail the course. Median. There is a question in the slide in the chat whether it's a median or an average. The answer is it's a median. Let me ask you a very simple question. Who knows what's the difference between a median and an average? And we are going to do it like this. I'm starting a poll. And please say yes if you know what the difference is between median and average. And please say no if you don't know the difference. Okay, so what we see so far is that 26 respondents have indicated that they know the difference between median and average. It's a good sign because, of course, data science, one of the important parts of data science is data analysis, and one of the parts of data analysis is statistics. So we will have quite some work which would be related to statistics. Okay, so let us continue. So of course, 2IMP40, so the course we are discussing now is not the only software engineering course, it's not the only course in our master programs. So how is it related to other courses? So there are no formal prerequisites. We do expect knowledge of basic statistics, so those of you who know what the differences between median and average are, kind of is good for them. I mean, we also expect a little bit more than that. If you do not remember what the difference between median and average, if you do not remember what linear regression is, if you have no idea what a p-value is, please check up your undergrad statistic books. For students from Eindhoven, students who got their bachelor degree in Eindhoven, they might check 2DI 90, which is a bachelor course on statistics. If you are interested in more advanced topics related to statistics, please consider joining 2DMT00, which is a master course, and it is being offered also in Q2. But of course, statistics is not all. So during this course, you will be expected to read scientific papers and to analyze them. So for instance, you will be given a scientific paper and we can ask you what research questions are being answered, what kind of research strategy has been used, and so on and so forth. You should also be familiar with modern software development. So modern software development doesn't necessarily mean the most recent framework or the most recent version of the framework, but it would be nice if you had an idea, for instance, how Git works or what kind of problems software developers experience when they are working in large projects. And of course, the foremost is genuine interest in software engineering research. So from the software engineering perspective, there are two courses which I need to mention. One of them is 2IMP25, Software Evolution, which is a course I used to teach for many years. but starting from this academic year, Eleni Konstantinou has taken it over. So this will be a revamped version. The course is offered in Q3, and it is related to IMP40 in a sense that both of the courses are grounded in the empirical software engineering field of research. The differences, however, is that IMP40 is focusing on methods that can be applied to study all kinds of empirical phenomena, and we are going to focus very much on the methods. IMP25 will focus on the insights which can be obtained by applying techniques such as we discussed here to study specifically software evolution. There is a question in the chat: will we use programming in this course? Nathan is answering. Maybe you can answer it.
Yeah, I just deleted my message because I thought you were going to answer it, but no, there won't be any programming requirement for this course.
Okay, good. Another course that I also need to mention is 2IMP00 Seminar Software Engineering and Technology. It's also a course in Q2. It is usually a course you take before embarking on the master thesis. And this is essentially an individual research project organized together with other students who are interested in software engineering topics. But during this seminar, you will be supervised by one of the members of the software engineering and technology research cluster. In practice, this means that depending on the topic you choose, you might be more or less exposed to empirical software engineering problems and subsequently to empirical research in software engineering methods. So if you would like to work with me, with Eleni, with Nathan, with a number of other colleagues, then it is very likely that you will be using those empirical methods. And of course, while we are going to talk about empirical software engineering, there are other parts of computer science that apply empirical methods. So for instance, if you plan to graduate in the security group, then several colleagues there are also using empirical methods. So data sources, sources of knowledge. We are going to use a book, Perspectives of Data on Data Science for Software Engineering, edited by Tim Menzies, Laurie Williams, and Thomas Zimmerman. There is no need to buy this book. The text of each and every chapter of this book is available on GitHub, and Nathan is going to post a link on GitHub. If you want to buy this book, feel free to buy. The proceedings of this book are going to the charity. Actually, Nathan has already posted the link to this book in the chat, so please check it. The only point is that in those chapters, the chapters are called based on the names of the authors, so you typically would not need to find a table of content somewhere in order to know which author has written the corresponding chapter. Otherwise, he will just mention it to you as we go. But again, buying this book is not mandatory. We are also going to use a substantial number of scientific articles. We are also going to use quite some other books. I'm going to put the references on the lower part of every slide, and you are going to see it in a moment as we proceed from the administration to more technical topics. So the last point I would like to mention is that this is the first time I'm teaching this course. So obviously, this means that there will be some problems simply because it's the first time. But at the same time, it's a great opportunity for you to influence how this course is going to look like also in the years to come, because your feedback is extremely valuable and will actually influence what are we talking about, how are we talking about, and so on. So please do not wait till the end of the course to fill in some kind of course evaluation form. It's much more tangible, it's much more valuable for me if you can respond as we go. If you prefer to do it anonymously, please do it anonymously. In any way and in any possible mechanism, I will be really grateful for you for providing feedback. This was it. about the administration of this course. Any questions from your side? As far as I understand, you cannot talk, but you can type. So please type if you have any questions. Okay, I see that Meda is typing. Can we attempt the quiz just once or more? I think that it's once. Nathan?
It's once, yeah.
Yes. Are the quizzes time limited? I think they are not, unless, well, you have to submit them by Tuesday, right?
Yeah, and I also think they are time limited, or for now the first one is time limited, where from the start you have 1 hour to answer it.
Ah, okay. You mean the Yasin asks, what preparation do you need for this test? You mean quiz, right? Yes, yeah.
Yeah, so for preparation, you need to study the material that was presented in the week of the quiz, and then you should mainly focus on the slides. It should be doable within 1 hour. Of course, we'll try to collect some feedback after the first one. So if you had a feeling that after the first one you really did not get through it within 1 hour, then please let us know. Or if you were done in 5 minutes, also please let us know, because yeah, we don't really know how long the quizzes will take, because we are more familiar with the material than you will be.
Yes, and of course the median also takes care that if one of the quizzes just goes astray, your median is highly unlikely to be affected. Okay, good. So the course is called Applications of Data Science for Software Engineering. And of course, you can combine those two expressions, data science and software engineering, in two ways. You can try to apply techniques from data science in order to understand software engineering phenomena, and you can also apply software engineering ideas in order to create better systems to support data science. For instance, there is quite some research on how to design machine learning systems, because of course machine learning algorithms do not exist in isolation, and they are usually a part of a larger software system. So essentially everything beyond the exact algorithm itself is not really machine learning, but it's a kind of software engineering. So this would be an example of application of software engineering for data science. This is not what we are going to do. What we are going to do, we are going to apply techniques from the world of the data science to solve software engineering problems. So how does it work? Here's a very simplistic schema. We start on the upper left corner with some kind of source of knowledge about software development. And the source of knowledge can be source code. It can be a version control system. It can be just the software developers themselves. Or it can be something like Slack, where developers communicate and discuss their project. So from all those data sources, we first of all need to collect data. happens very rarely in software engineering that your data just comes to you ready and prepared, and you can just happily analyze it. Collecting data is a skill on its own. And this is where we are going to talk about things like mining software repositories, like interviewing, like conducting surveys, and so on and so on. This is a part of data collection. Once you collected your data, of course, you somehow need to analyze it. Because otherwise, you just have your data and you don't know what do you have there. So analysis techniques usually can be divided into qualitative and quantitative. Essentially, quantitative would be all about counting, qualitative would be all about understanding what people are talking about, what is going on. We are going to see examples of those techniques at the second half of the course. So the first half of the course will be mostly about data collection. The second half of the course will be mostly about data analysis. And of course, once we analyze this data, we need to interpret it. So it's important to convert the results we have obtained at the side of the data science back to software engineering. It is not enough to know that variable X influences variable Y. We need to know what does it mean for software development projects. Do we need to involve more people? Do we need to use different technology? Do we need to use different testing strategies, and so on? So based on this kind of interpretation, we're typically going to design interventions. So we're typically going to design, to provide recommendations how to improve the software development process. In a way, software engineering can be seen as action research. What we are trying to do, we are trying to improve software development process by understanding it and by analyzing what we observe. So what does it mean in terms of questions and goals? So from the perspective of software engineering, the goal is to obtain empirical evidence about what works in software engineering and what does not. For example, does test-driven development really work? Because there are lots of people who say test-driven development is the most important thing which has been invented after the warm water. There are people who say, I don't care about test-driven development. Is it the case that some programming languages essentially make better programs than others? You probably have seen those infinite flame wars online for people supporting language A as opposed to people supporting language B. Where do most software flaws come from? Why are my code reviews not finding any defects? So all those questions are typical software engineering questions. And the goal of empirical software engineering, which is essentially what we are going to do, is to obtain empirical evidence about what works in software engineering and what does not. From the perspective of data science, application of data science to software engineering is quite interesting because this is an opportunity to design tools and techniques for data which is reasonably large. Of course, you just a couple of examples, right? GitHub has 100 million repositories and 40 million users. Stack Overflow has 18 million questions and almost 30 million answers. Of course, it's not comparable to terabytes of data produced automatically by telescopes, but keep in mind that this data is mostly produced by people. So there is a certain authenticity to it, and it is much more interesting in many, many ways. This data is highly diverse. Independently from what data source you take, you will sooner or later find that there are structured elements such as metadata, who has performed a commit, when the commit was performed, and so on. But you also have source code, whether it's an example of Stack Overflow or entire project on GitHub. You typically have natural language texts, which can be, for instance, code review discussions, questions on Stack Overflow, but also interviews, or actually transcripts of interviews if you are interviewing a software developer. Very often, software engineering data contains schemes and diagrams, so visual elements. whether it's a user interface snapshot or a UML diagram. It's a data which is difficult to analyze. And in some cases, it even contains videos, for instance, YouTube instructional videos. These data sets are typically publicly available. So GitHub has 100 million repositories. Of course, most of them are not publicly available, but 28 million of them are. And it is quite a substantial amount of data which we can analyze in order to answer software engineering questions. And finally, it is rapidly evolving. Every single day, there are more questions, there are more commits, there are more projects. So whatever analysis we perform today might produce different results as opposed to an analysis I performed 3, 4, 5 years ago. So our field belongs to software engineering, but it builds on the techniques and tools borrowed from data science and adapted from data science. But before we go there, as I already said, our goal was to obtain empirical evidence. And this, of course, calls two questions. Like, why do we really need evidence? And what does empirical mean? So the evidence is needed because of the reality check. And if you think about it, lots and lots of software engineering solutions were based essentially on good intentions of developers, or maybe on some ideas of those developers, how the world should look like. So for instance, if you are saying, I need to find bugs in my code, then a typical consultant will come to you and tell, use our new testing environment or use our new tool to find those bugs. But then, of course, this would also require retraining all the teams. So how nice this testing environment might be, if it's not accepted by people, then something is wrong. And the same example can be made for all other fields. Let's take another one. Like, how can I reduce the resources needed for testing? Testing is expensive. We all know that we need many testers to test and ensure quality and so on. So the standard question would be use a model checking, because once you use model checking, you don't need to test manually, right? Moreover, model checking can prove absence of errors as opposed to merely finding them. But of course, it's not obvious, because to apply model checking, you need training. It takes too long. Lots of realistic software systems cannot be model checked because it simply it takes unreasonable amount of time. And if you are applying model checking not to the source code itself, but to models, then those models do not necessarily capture the intention or have to be constructed based on the source code. And again, correspondence between those models and the source code is not necessarily obvious. So in general, reasoning and intuition a priori are not necessarily agreeing with observations. And this is the focus of empiricism. So empiricism, as some of you probably know, comes from the Greek word empiria, which means experience. So empirical research assumes that observation is the only definite source of knowledge. Reasoning or intuition can be source of belief or can be source of conjecture, but those beliefs and conjectures should be verified by a follow-up empirical study, by a follow-up observation. In software engineering, this means that researchers do not describe how software should be developed, but researchers describe how software is being developed, with the goal of suggesting better practices or best practices on how to develop better software in terms of product, or how to develop software better in terms of process. On the right, you see an illustration by Tom Dunn from American Scientist in 2011. And this is essentially the summary of empirical software engineering. So you have a microscope, and on the microscope glass, you have software developers who are working, and at the same time, they are being observed by researchers who are on the upper side of the microscope. And if you look carefully, you also see a ruler that one of those researchers is holding. And this is because empirical research often requires measuring things, measuring projects, measuring processes, measuring people. This will also be an important part of our discussion. Of course, by the very same token, the very same image conveys a whole bunch of concerns related to the need of performing observation, such as privacy. It is very nice if you position yourself among the researchers on top of the Microsoft tube. It might be less nice if you are positioning yourself among the developers on the microscope glass. So when we are going to talk about research methods, we will definitely touch on topics related to privacy and ethics in general. Empiricism is, of course, not the only view on software engineering. A competing view is rationalism. Rationalism comes from Latin, from ratio, which is reason. And the foundation for rationalism is that the knowledge can be obtained by intuition and reasoning. Some rationalists also believe that knowledge can be obtained by observation, but then this observational-based knowledge is inferior to one obtained by reasoning. So in software engineering, this means that rationalists will design methods and guidelines how to develop software based on the reasoning, based on how things should be done in order to achieve things. So on the right-hand side, you see the famous V model. I guess that you have all seen this V model in your undergrad software engineering class. So this is how software is supposed to be developed. You are starting with business requirement specification. You are going to system requirements, high-level design, low-level design, and so on. And then on the right-hand side of your V model, you see the validation phase, which every single phase matching the corresponding phase at the development side of the V cycle. This is how software development should take place. So the word should indicates this is a prescriptional model. This is a prescriptive model, sorry, based on reasoning. It's not based on any kind of observation. It is not necessarily based on any kind of observation. It is based on reasoning how things should be done. So if you are going to juxtapose rationalism and empiricism, we are going to see that the opinions of rationalists and empiricists tend to be quite orthogonal. For instance, when it comes to methods, rationalists believe that developers use methods. For instance, developers use object-oriented design as a method, or developers use test-driven development as a method. Empiricists will typically say developers rarely use methods as intended, if at all. Just to give you an example from my own practice, right? Agile development was, of course, very, very popular in all kinds of companies. In one of the companies, I went and I talked to them. They said, yes, we are also doing Agile. And then I asked them, okay, how long does your sprint take? And the answer was 6 months. So as you can imagine, this was not exactly the intention of the designers of the original ideas from Agile Manifesto. But this is what we see in practice. Developers rarely use methods as intended, if at all. And I will also add here, and they have very valid reasons to do so or not to do so. When it comes to requirements, in the rational view, developers elicit requirements from the user. So we have a user, the user has a perfect understanding of what they want to achieve, and the goal of the requirements engineer is to interview the user and elicit requirements. According to the empiricists, developers essentially make sense of a problematic context. There is no very clear ideal view of the thing that somebody wants. The goal is to try to understand in what sense this software which has to be built software has to be built should fit the context of where it is supposed to be operating. I'm going to skip the notions of success and design. They are on your slide. I would like just to say that from the perspective of a rationalist, development solves problems. From the perspective of empiricist, there is no such a thing as the problem. The software development cannot solve the problem because there is no such a thing. There is a context where a software system is supposed to be operating, and for some actors, this context might be problematic. Of course, different actors can interpret this problematic nature from in different ways, subsequently leading to contradictory requirements. Right? So developers need to make sense of this problematic context. And to summarize all this, rationalists will typically be prescriptive. So they will put a focus on how software should be developed. If you open a typical software development book, this is what you're going to see. Empiricists are going to discuss how software is being developed. So they are descriptive. If you look at your traditional undergraduate software engineering course, you will probably find that many things we are talking about are on the rational side. Typical software engineering class teaches you to elicit requirements from the user. It will explain that once requirements have been elicited, you have the design phase, and that ultimately the success of a project would mean that we have a scope, we have budget, we have schedule, and once we have delivered, given those three constraints, this triangle, right, we can say that our project is a success. Empiricism tries to take a different view and tries to focus on how things happen rather than how things need to happen. So I would like to stop at this point. We have almost finished our first hour, and we are going to reconvene at 2:30, and I'm also going to stop the recording at this point. See you in quarter an hour. Okay, welcome to the second hour of our first lecture on applications of data science to software engineering. In the first hour, after we have extensively discussed organization of the course, I have introduced two dominant views on software development, rationalism and empiricism. You see the summary of those two views on the slide. Very simply put, rationalist is typically prescriptive, empiricism is typically descriptive. So why do we actually have this discussion? Why do we need to know about those views? And this is because not all questions which we can ask, not all research questions we can ask, can be answered as part of rationalist or as part of empiricist paradigm. So one of the first skills which you need to develop in this course is to figure out whether this is an appropriate empirical question. Not all questions are appropriate for empirical science. Yes. So here is the first question. What is the lower bound of the combinatorial complexity of the fastest possible comparison-based sorting algorithm? Sorry, comparison-based sorting algorithm. So again, let us start a poll. And the question is, this question is appropriate for empirical studies? Yes or no? So we have 22 responses. I kind of wonder what happens with the other respondents. So what happens now is that 17 of you decided that this is not appropriate for empirical study, and 5 decided that it is. I personally believe that it is not appropriate for empirical study because this question refers to any theoretically possible algorithm. So we cannot actually answer this question by observation. In fact, to answer it, we need some form of mathematical reasoning, which means that this question makes sense from the rationalist perspective, but does not make so much sense from the empirical perspective. Another one, do managers' claims about how often they use UML correlate with the actual use of UML? And again, the same question, is this question appropriate for empirical studies? Right. So it seems that in this case, we are almost unanimous. There is only one person who thinks it's not appropriate, but most of you do think that it is appropriate for empirical studies. Indeed, this is a question which can be answered by observations. We need to observe claims of managers, we need to observe the actual use of developers, and we need to compare. This is a classical empirical question. The last one, what is an effective way for teams to represent design knowledge to improve coordination? And again, the same kind of question. Are we talking here about an empirical question or not? Okay, so we have received 22 answers. Here you see the poll results. You see that in this case, the opinions are more split. And essentially, the tricky part here is that this is not really an empirical question, but it's also not a rationalist question. It's a question about design. So essentially, the question is how to design a way to represent design knowledge in order to improve coordination. Whether once you have designed this particular way of representing design knowledge, you can evaluate whether it is effective or not, and then this would be an empirical study. But the question about design is not really a question about knowledge. It's a question about how creating things, right? So in this course, as you probably have guessed, we are going to adopt empiricism. This does not mean that rational questions do not have right of existence. They do. There is a lot of research which is rational in nature. There is a lot of software engineering research which is rational in nature, but this is not what we are going to look at. And there is, of course, obvious reason why I am showing this wonderful picture here, because proof of the pudding is in the eating. Only by trying the pudding can actually understand how to make better. And often making the pudding better will not involve a typical rationalist solution. Here is an example. Again, how can I improve requirements? One of the questions we have seen during the first hour, so a rationalist answer would be use this. So for instance, in this case, use a controlled language, which would restrict your language to certain verbs, certain nouns, and so on. And subsequently, people might be unhappy because they cannot express what they want given those restrictions. But an empirical researcher, instead of providing a solution, will typically be asking questions. So, for instance, if you want to improve your requirements, how do you write those requirements? Are those requirements clear? Are those requirements complete? And depending on the answers we are going to get, we can try to ask follow-up questions. For instance, if the requirements are clear but incomplete, maybe we are not getting enough information from our customer. So how often do you meet the customer? And again, I am very careful in phrasing, maybe we are not getting. This is not a claim, this is a conjecture. We are putting this conjecture forward and we are verifying it by asking our counterpart. And then, of course, the solution here might be simply to schedule more frequent meetings with the customer rather than using a new solution. So what does it mean for our course? Since we are going to adopt empiricism, we are mostly going to talk about topics like how to collect the data and how to analyze the data. So the first part of the course will be about collecting the data. We'll start with talking about it next week. And then the second part of the course will be about analyzing the data. So before we actually start talking about those research strategies and research methods, I would like to show you 5 empirical studies. Looking at the time, I don't know whether I will have enough time to discuss all 5 with you. And essentially, when talking about each one of those studies, we are going to see what problems was studied, what methods were used for data collection and data analysis, and we are going to see what kind of results have been obtained. So this is the first study. Any ideas what it is? Any business? Just type. Okay, I see that multiple users are typing. That's good. Play Store reviews, Apple Store reviews, indeed. So this is an Apple Store reviews. It doesn't matter which app store is it. And here we have reviews of one of the apps. Actually, this app is Pages. So the question that the researchers wanted to answer was why do users give low ratings to an app? So here I have highlighted some of those low ratings. You see some low number of stars, 1 or 2 stars, and there is some explanation. So how have the authors decided to work to address this problem? So they have selected apps and they have selected those which have low rating and high rating. They picked 20 most popular iOS apps and they defined high as having 3.5 stars or more, and low as 3.5 stars or less. So they collected all the reviews of those 20 apps. And then they specifically focused on reviews which have only 1 or 2 stars, because this is what they want, right? They want to understand why users give low ratings. Of course, they got lots of those reviews, more than 250,000. So analyzing those reviews manually was not possible. So they have selected a statistically significant sample. We are going to talk about sampling on next week, Tuesday. So if you don't know what statistically significant sample means, don't worry, I will explain it. And they have ultimately have considered 6,390 reviews that have been analyzed manually. So if you see those figure of a human being on the slide, this means that the step was performed manually. So they've been taking the reviews in order to understand what are the reasons for complaints. If they have found a new reason for complaints and essentially went back and tagged more and more reviews. And once all the reasons for complaints from this data set have been identified, they have completed their study. So the reasons were that primarily the issues we see here, the user saw with those apps were related to functional errors, to app crashing. Sometimes features that the users used to like have been removed, and sometimes the users missed those features they wanted. So if you look at the formal results, you see here most frequent results. and most impactful ones. The most frequent problems were related indeed to functional errors, which are essentially bugs, requests on new functionality, crashes, network problems, and so on and so forth. If you look, however, frequency is of course one way of looking at complaints. Impact is another one. So impact is the relationship between number of 1-star reviewed and 2-star reviewed. The idea here is that if something forces the user to give 1 star, then they are really, really unhappy about the app, as opposed to someone who is giving 2 stars. So for instance, if you look at the category, which is called privacy and ethical, then you see that in terms of frequency, it appears on the rank number 9, while in terms of impact, it is number 1. So essentially, this means that if an app exhibits some problems related to privacy and ethics, then it is much more likely that the user will be profoundly unhappy and give 1 star instead of 2. So just to give an example of privacy and ethical considerations that the users were complaining about was something like app that thinks your Facebook contacts can be used for whatever purposes the app wants. So this is typically a thing that users do not like. So if you see if you look at the ranks, you will see that the most common issues are functional errors, feature requests, app crashing, and network problems. But the impact is completely different. You see that the impact is related to things like privacy and ethics, feature removal, hidden costs, and apps crashing again. So essentially, app crashing is the only one which is on 2 lists. The tricky part here is what developers actually can do. If you look at the most common errors, then many of them can be directly addressed by developers. If you have a bug, you just fix it. If you see your app is crashing, you just fix it. But of course, feature request is already more problematic. If you have a large company which produces lots and lots of different apps, you cannot necessarily decide on your own as a software developer which features to implement. So software developers might influence development of new features, but it is not completely their only task. The situation with most problematic, most impactful concerns is different. Among those 4, app crashing is the only one which can be directly addressed by developers. Feature removal, in a sense, is very similar to feature request. It's a matter of strategy. It's a matter of how the company plans to evolve their software system. So again, developers might influence it, but it's not something they typically decide upon. While, of course, the last ones, such as privacy and ethics and hidden cost, are essentially related to the value of the app itself. An example of a hidden cost would be costs which are incurred by the functionality of a free app. For instance, you have downloaded an app which is a game, and it's free, but in order to progress sufficiently fast, or in order to progress at all, you are being required to purchase some kind of game coins or gems or whatever, and the only way of purchasing those coins and gems is by paying real money. So these kind of decisions are outside of the developer's control. So based on this observation, the authors recommend developers not merely to focus on the most common issues, but on most impactful complaints. And while this is often outside of developers' control, they should create awareness within their company of what affecting perception of their app by the users. So looking at our study, what kind of data analysis or data science techniques have been used? The first step, as I told, the researchers have selected 20 popular iOS applications, and then they have collected reviews, user reviews corresponding to those applications. This step is known as archival data analysis or mining software repositories. So software repositories, typical software repositories is something like version control, issue tracker, but in this case, it's an app store. It's a software repository as well. The next step they have performed sampling. The problem that they have faced was that they have too many user reviews to perform the following step. So they had to reduce the number of artifacts they want to analyze, and this step is sampling. Again, as I promised you, next Tuesday we are going to talk about sampling. And then on the data analysis side, they have performed a procedure which is known as open coding. So they have received text and they have manually analyzed what this text is about. Okay, let us look at the next study. The next study tried to understand how to make a good day of a software developer typical and how to make a typical day good. So this study has been conducted by colleagues at Microsoft Research. So what have they done? They have started with an existing taxonomy of software development activities. Then they have conducted interviews with developers in order to refine this taxonomy and understand how developers spend their days. Based on this, they have designed a survey, and to be sure that this survey is correctly interpreted by the respondents, they have piloted, meaning that they have sent it first of all to 800 invitations. They first of all sent 800 invitations, asking questions like, was the previous day typical, good, and why? And in this way, they essentially also figured out whether the questions are correctly understood, whether they're clear, whether there are possibilities of ambiguities, and so on and so forth. Once the survey has been piloted, so once the authors were sure that the questions are correctly phrased, they have actually used it on a much larger scale. So they have designed a survey. They have sent more than 37,000 invitations, 500 invitations per day during 4 months, and they have obtained almost 6,000 responses. So then they dropped responses that did not provide an explanation and identify recurrent themes in those explanations. What have they found? They have found that the good day or bad day depends on the perception of developers, whether they are productive, whether they experience time pressure, whether they have overtime. It also depends on whether they think that this day is contributing to creation of value for their company, or value for themselves, or value for somebody else. It's important for developers to feel that they're making progress, that they have constructive discussions, they're learning new things, and so on. And at the same time, it's about efficient use of time. For instance, ability to work in a focused way. In a similar way, the typical day is essentially related to the match or mismatch between the expectations and reality. This mismatch is influenced by time spent on activities. So if you expect to spend the entire day on programming, but you only have meetings, then this day will be atypical. But of course, in its turn, how much time you spend on what activity depends on your primary work tasks, on your private life, on your location, because people at different locations have different issues, different tasks, and so on and so forth, all the way to the project phase. Because of course, at different project phases, we have different types of working days. If the project is, for instance, in the initial phase, then it is more logical that we'll have lots of meetings defining the primary outline for the project, as opposed to a project which is established and essentially finalized. So the recommendation in this case would be addressing the managers who are being called to make good days typical and make atypical days good. So making good days typical would mean introducing more routine. For instance, by reducing interruptions, reducing meetings which are not necessarily necessary, minimizing administrative tasks. At the same time, if you are talking about atypical days, then those would be better good. For instance, allow people to work from home when one needs a lot of focus and attention. So this study, of course, has been published before the current pandemic, where the entire concept of working from home had to be rethought. Allow people to have no meeting days, such that they can focus on things they like more, such as software development, and so on and so forth. So how was the study conducted from the methodological perspective? Again, we see two clear phases: data collection and data analysis. At the data collection phase, the researchers have started with conducting 10 interviews. You might remember that they talked to 10 people, and then they have conducted a survey. At the data analysis side, we again see the open coding, meaning analysis of free-form text, which has been provided by the survey respondents. The next study is a completely different one, and this one was focusing on cognition, on how our brain works when we are writing prose as opposed to when we are writing code. This is a research method. So you already see a large picture of an fMRI in the middle of the slide. So it's a functional magnetic resonance imaging. Some of you might have experienced it in the medical facilities. Here it has been used to understand which parts of the brain are being activated when specific tasks are being performed. And those specific tasks are related to programming and to writing prose. So how did the research go? So first of all, the researchers have conducted their participants, who were students, and they collected some basic demographic data, such as gender, age, biological sex, and so on. And they have also performed several standard psychological measurements. Because those participants were students, it was extremely important to ensure that they all have comparable level of programming knowledge. This is why the researchers have administered a programming quiz geared towards C and C++. Then participants have been trained. As you can imagine, it doesn't come very naturally to you to program while laying in the fMRI machine. So, of course, participants had to be trained in order to perform the study. And then the experiment itself was conducted. So participants have received 17 tasks related to filling the gaps in prose and 9 in free form. The same for code. I'm going to show you the tasks in a moment. And the order was random. So the measurements have been performed. fMRI data is known to be noisy. It has been cleaned. Statistical analysis have been performed both within the participant and between participants, because of course we want to know not only whether the individual person behaves differently when it comes to prose as opposed to when it comes to code, but also whether we can conclude something generic for the population in general, and the results have been visualized. At the same time, they have also conducted a post-experiment survey to understand how developers experienced the entire setup. So this is a very brief show on the tasks. So remember, we had prose versus code. So prose are the two images in the upper part of the slide. Code are the two images in the lower part of the slide. On the left, we have fill in the blank, which is essentially a sentence with omitted word, or source code with omitted fragment. On the right, we see a long response kind of task, which is a typical essay, small essay assignment in case of prose, and a simple programming assignment in case of the source code. So what are the results? Here we see the image of a human brain. So the two leftmost images show the left hemisphere, two rightmost images show the right hemisphere. The areas in which I highlighted here are so-called Brodmann areas. There are more areas discussed in the paper, but I just wanted to show you those one. And the interpretation goes as follows. Colder colors, so green and blue, mean that this area is more activated on the prose-related tasks as opposed to code-related tasks. Hot area from red to yellow means that this area is more activated during the coding tasks as opposed to prose. So what do we see? We see that when it comes to prose writing, it is typically associated with areas which are traditionally associated with language. So you see the so-called Wernicke's area on the left, which is typically related to language and to comprehension, most often listening comprehension, but language comprehension in general as well. When you look at the coding areas, well, areas which are more active during the coding, then you see things which are related to attention, which are related to memory, and which are related to spatial cognition. Essentially, this means that the brain does not treat code writing as prose writing as similar. Those are different activities. Weirdly enough, during the post-experiment survey, respondents tend to report similarities between code and prose, between writing code and writing prose. So essentially, our brain tells a different story than the respondents themselves. The authors conclude here that the self-reporting is essentially unreliable. And this is the most important message of the study to the researchers. If they want to understand how people code, how people write code, it is not enough to base this kind of analysis on surveys, and we need to augment it on some kind of objective data analysis, such as an fMRI scanner. So what does it mean in terms of methodology? What have we seen? What have we seen is the following. Again, we see a clear separation between data collection and data analysis. On the data collection side, the process we have seen is known as a controlled experiment. It involves elements of a survey, but it is predominantly controlled experiment. We are going to talk about controlled experiments in lecture 7, so we'll see how those things are being designed, what kind of problems are there, and so on and so forth. When it comes to the data analysis, we see yet another typical combination for many papers. We see a combination of statistical analysis and visualization. So I have shown you the visualization, which was based on differences between those activations of different brain areas, but to observe those differences, the authors have performed statistical analysis. A very brief discussion of the next study. So the next study was related to how developers ask for help. So in this study, the author Paige Rodeguero from Clemson University went to a company and essentially observed what was going on there for 2 months. So she was looking at what tasks are performed by developers. She even participated in lunches. She has interviewed lots of people. She has even took pictures from tasks and meetings. And based on this extremely rich data, she has identified recurrent patterns. For example, she has observed that programmers are more willing to help others during lunch breaks. And at the same time, they are more likely to ask for help if the problem is being perceived as important, but at the same time, less likely to ask for help if the colleague seems busy. This can be problematic because sometimes programmers would wait days and days for response to an email, even if they saw their more senior, more busy colleague throughout the day. They would not dare to say anything because of the concern for someone else's schedule and obligations. Newcomers feel less comfortable asking for help, but are still quicker to ask for help than more senior people. So it is interesting that newcomers are less comfortable but dare to ask questions, while experienced developers don't really report being uncomfortable, but essentially do not dare to ask. So again, understanding what are the barriers and how people communicate is non-trivial. It's not just newcomers always ask more questions, or more experienced always ask more questions. So the recommendation here would be for tool builders. Tool builders should consider building tools indicating who is available to provide help. Because if I need help and I need the help from somebody else, I might be concerned that this person is too busy, and I would not even dare to ask a question. So in terms of methodology, what do we see here? What we see here is a data collection method which is known as ethnography. In this case, the researcher went and immersed herself in the company. And then based on this ethnographic research, she has identified recurrent patterns in the community and in the local culture. So ethnographic research in software engineering is not very common for obvious reasons. It's a very, very expensive form of research. So just imagine that you need to decide for several months, I'm joining a project, I'm attending every single communication, I'm trying to be there non-stop. But of course, when this kind of research is being conducted, usually the results are insightful and valuable. The last study I want to talk to you is one of the studies I have conducted together with colleagues from Carnegie Mellon, is what projects are more beneficial for women to join. So in this case, what we have done, we have started with analyzing GitHub data. So we have sampled 300,000 users. So this again is a sampling thing because of course GitHub has millions and millions of users. And specifically we have used a tool which guessed, with also concerns related to this guessing, the gender of those users based on their names. And then we collected a balanced sample of almost 30,000 women and almost 30,000 men and all their projects. Using this sample, we have conducted statistical modeling, both Cox regression and logistic regression as statistical techniques. And on top of this, we have also created a small sample of 1,000 users that we have surveyed. Of course, in order to create this balanced sample, we had to, first of all, build a tool which was capable of guessing names or guessing gender based on names. So the result of the statistical analysis were as follows. So what we have here is a statistical model. The early stage means it's a logistic regression. That means that contributors who disengage within the first 3 months of their activity. Later stage are contributors who disengage after 3 months of the activity, and we have used a different modeling mechanism. So the interpretation of those coefficients works as follows. If the coefficient is less than 1, then the corresponding variable means the more of this variable, the less likely to disengage. If the coefficient is more than 1, then the more of this variable, the more likely to disengage. So what do we see here, right? So we see that, for instance, followers have a coefficient which is 0.61. This means that the more followers a project have, the less likely developers are to disengage. So the same holds for more active projects based on the number of commits and more versatile projects. This is related to the variable which is called a niche width here. We also see that, as expected, women disengage faster, right? So if a person is a woman, then they are likely to disengage faster as opposed to than if they are a man. The coefficient is greater than 1. What is also interesting here, we see that language heterogeneity, so essentially presence of multiple programming languages within the same project, has a coefficient lesser than 1, meaning that the more heterogeneous the projects are in terms of programming languages, the less likely are the contributors to disengage. And this is exactly what we see on the image on the right-hand side. So we see a difference in survival probability between individuals who are involved in projects with high and low programming language diversity. And we see that this curve is always positive. So the more, this means that survival likelihood for those who are involved in highly language diverse projects is higher than for those who are involved in low language diverse projects. Moreover, there is an interaction between language and gender, language heterogeneity, and gender. And again, you see that the coefficient is less than 1. This means that this interaction is positive for disengagement. So what does it mean? Again, look at the picture on the right. While people of any gender benefit from contributing to projects with many programming languages, women benefit from it more. At least women benefit from it more, starting from roughly 12 months from the beginning of the project. So let us look at the methods which have been used here. Again, in this study, we have started with archival data analysis on mining software repositories. Then we have performed sampling. To perform this sampling, we had to build a classifier, we had to build a tool. And then we have concluded this study with a statistical analysis and with a survey. So let me summarize the 5 studies we have discussed. You see here that they have used different data sources, used different data collection and data analysis mechanisms. They provided different kinds of recommendations for different beneficiaries. But whatever empirical study you're going to conduct, you need to keep those things in mind. Who are your beneficiaries? What kind of recommendation do you want to provide? And in function of this, what data sources are you going to use? How are you going to collect the data? And how you're going to analyze the data? Of course, answering those questions, which methods to choose, will be a topic for our upcoming lectures. So specifically on Thursday, we are going to talk about research strategies. Research strategies are not research methods. Each strategy is typically implemented using one or more research methods, but they typically allow you to position your problem in a specific context and to see what kind of conclusions you can derive depending on what kind of handlings you are allowed to perform. Each one of those has their own advantages, disadvantages, and we are going to discuss them quite extensively on Thursday. As I already promised, Tuesday will be a lecture. Next week, Tuesday, will be a lecture about sampling. So essentially, how do we go from all those projects or all those people in the world to something which is manageable? How do we know what project to analyze, what people to survey, and so on and so forth? Specifically, talking to people will be a topic for the 2 lectures. After the sampling lecture, we will start by discussing interviews, and then we will move to surveys. In several studies we have discussed, the first step was archival data analysis, also known as mining software repositories. And we'll have a guest lecture by Dr. Leni Constantinou, who is going to talk to us about mining software repositories. And then, of course, in the second part of the course, when we are going to talk about data analysis techniques, we are going to talk both about statistics and about qualitative analysis, a typical example of which are the open and closed coding. So very briefly, if you are interested in this kind of research, please feel free to talk to a whole bunch of empirical software engineering people and empirical people in general. You see several names on the slide, And you also see that, for instance, Luca Allodi from the security group is also an empirical researcher. So what have we done today? We have agreed that this course is about applications of data science to software engineering. So if this is not if you expected something else, then unfortunately this is what it is. We talked about two dominant views, empiricism versus rationalism. Keep in mind that for empiricism, the observation is a primary source of knowledge. You can use intuition and reasoning to form conjectures, but those conjectures should be validated or refuted through observation. For rationalists, it's exactly the other way around. Rationalists believe in intuition and reasoning. Some rationalists are ready to accept observation as a source of knowledge, but this is usually a secondary knowledge which can be used to support things, but it's not really the primary mechanism of creating knowledge. Not all research questions can be meaningfully asked or meaningfully answered in all paradigms. So neither of the two is the silver bullet. Depending on what you want, you need to take either one worldview or another one. They have seen a series of studies, 5 studies, which used a broad spectrum of data collection and data analysis techniques, from repository minings to controlled experiment, from interviews to ethnography. And when it comes to data analysis, statistical analysis, visualization, open coding, machine learning, many of those techniques are going to be subject of follow-up lectures. And of course, if a certain topic is not covered by the lectures, please reach out to me, and I can either recommend you a book or a podcast or a YouTube video which you might find useful if you would like to learn more about specific research methods or about specific kinds of research. This concludes our discussion. I see now that there is one question in the chat. So the question is, if 38, so this is a question about the controlled experiment with the fMRI. So if so Yuri asks, if 38.5% of the respondents report similarities between coding and writing prose, shouldn't the remaining ones have reported that they are different? Thus the survey has the same result. Well, I think it's a matter of how do you interpret the survey having the same result. Essentially, this doesn't necessarily mean that the remaining ones do not report differences. It essentially means that the remaining ones do not report similarities. It also means that in this particular case, the survey has shown a much higher degree of disagreement between the people, in a sense that while the empirical, fMRI data has clearly shown separation of those brain areas and those activities, a significant part of respondents actually believed them to be similar. So the survey has given a more fuzzy picture in a way. I hope this answers your question. If you have any questions to me, feel free to ask either here or on Slack. And I'm going to stop the recording now.